Okay. All right. Okay, so conductance. Conductance. Here we go. All right, so conductance. Okay, so this is going to tie in two different things that we've studied. So one, we're going to bring back ideas from this lecture. So conductance is going to be a sort of similar, but something different from expansion or sparsity. Sorry. And otherwise, it's also going to build on some of the random walk stuff from last class and from the last few classes. And in particular, we're going to be making use of this theorem from the end of this was what we tried to prove last time, which was that if the random walk matrix has eigenvalues 1 down to -1, and we know it does because it's similar to a symmetric matrix, the normalized random walk that'll come up again later, then we can bound how fast the random walk will converge to the stationary distribution. Roughly kind of exponential and gamma, where gamma is the difference between that first eigenvalue 1 and the biggest absolute value between the second eigenvalue and the nth eigenvalue. Okay. Now, some level what's going on, it was just like a diagonal matrix that was just spinning and spinning. That was sort of the non-stationary part of it. And if all those eigenvalues, all the other eigenvalues had absolute value much smaller than 1, then that spins down to 0 all the faster. So, okay. All right, so today's lecture is going to be a little bit more combinatorial than last time. In particular, it's going to help connect some of these algebraic things to more combinatorial ideas. So conductance is a graph property, a combinatorial graph property, not defined in terms of matrices. And then we're going to have this very interesting thing called Cheeger's inequality, which will relate this graph property conductance with some eigenvalue type stuff. And then we'll get something about how fast we converge to a stationary distribution as a function of conductance. Okay, which is kind of nice because conductance is maybe easier to think about conceptually. It's more intuitive than the second eigenvalue of the Laplacian or something, right? That's just some algebraic thing. It doesn't mean so much physically because we don't have much analogy. But conductance, when I give you the definition, you'll understand what it means. It'll be easy to see. And we'll also have an algorithm for getting low conductance cuts, which will use all of these concepts. Okay, so this is hopefully bringing it back into slightly more comfortable space. Okay, so let me just remind us of what we once did. This is slides from before. This is the sparsest cut problem. And there, we had these like edge, it was like a flow problem, cut problem. So we had edge capacities and we had demands, thinking of like pairs we wanted to connect with paths. And the sparsity was defined as, the number of edges that I'm cutting was a set divided by the number of pairs I'm splitting up. So that was the most general formulation, but maybe the simpler one is just when we just do all pairs of vertices, in which case the sparsity of a graph is, a sparsity of a set is kind of like, how many edges am I cutting divided by the total number of pairs of vertices getting split up. Okay, so this has a lot of algorithmic applications, but also it's just a kind of structural thing about graphs, right? So in a graph like this, which is roughly 2 clicks, there's a few edges in between, it's going to have relatively low sparsity because I can kind of split it pretty much in half and divide the vertices in half and disrupt a lot of pairs while removing relatively few edges. And one reason I had this example before is because in some sense, if you had asked for the minimum cut in a graph, you'd just be trimming off one vertex. That's really not very useful from, say, a divide and conquer standpoint, whereas dividing this graph in half does clearly give you a little bit more progress. Okay, so the notion of conductance is okay, and then just to remind you, just building on this, we ultimately gave a approximation algorithm for sparsest cut, which was sort of based on line embeddings and stuff like that. Okay, so all right, before defining some stuff, let me just get some notation out of the way. I don't think any of this is too new, so maybe it's just a reminder. But we're going to be working with an undirected graph with some positive edge weights. I'm using kind of delta of S to be the set of edges cut by S, which means W of delta S will be the weight of the cut. Well, maybe one new notion is we're going to be focusing on volume. So the volume of a set of vertices is the sum of degrees of the vertices. So like the total number of incident edges. If an edge is inside S, it kind of gets counted twice. The edges in the cut get counted once. Okay. And then S bar is just the complement of S. Okay. All right. So then conductance. Okay. So and I have some examples coming up. So compared to sparsity, so conductance is defined. The conductance of a set S, of a set of vertices S, is well, I guess I should have drawn a picture, but luckily I still can. Okay. So here's my set S. Okay, and I'm looking at the weight of the edges cut by S, okay, divided by the total volume, which is like the sum of degrees in S, okay? Especially if S is the smaller half. So if S represents less than half of the volume of the graph, then you don't have to worry about the min, it'll just be volume S in the denominator. Okay, so fine. And the conductance of the graph is the minimum conductance over all sets S. Okay, so the real difference from before is that we have volume in the denominator instead of the number of vertices. Okay, one thing I should point out is before in the other class it was convenient to do something like, okay, so we would do something blah 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 divided by number of vertices times the number of other vertices, right? But this is roughly 1 over n times the minimum of the two. Okay, because I know that the bigger one, whatever is the bigger one, I know it's at most n, and it's at least n over 2, right? So really the extra factor, we kind of know the value up to a factor of 2, we're going to be working with approximations anyway. So there's really no strong distinction between worrying about the min and the product. It's just so for some problems, one's slightly more convenient than the other. Okay, but one converts to the other and you only lose a factor of 2, so we won't make that distinction too much. Okay, so maybe just to get some sense, okay, so I rewrote sparsity in terms of min, but again, that's not a big deal. So here's 3 different graphs, and I was going to ask you guys for each one, whether this is like high sparsity, medium sparsity, low sparsity, loosely speaking, high conductance, medium conductance, low conductance kind of thing. Okay. So I guess, what can we do? You can do votes. Okay, who's not going to vote? All right. Okay. So I'll start in the first column in sparsity. Who feels like this has high sparsity? Okay. Who feels this has like sort of a medium sparsity? Nice, 1. And who would say this has pretty low sparsity? And -1. Okay. And what about conductance? Let me put it this way. Would anyone change their answer? Okay, who feels like it has high conductance? 1. Who feels like it has medium conductance? And who feels like it has low conductance? And -2. Okay, fine. Move to the second column. Okay, so the difference now is that one side is actually is like a very sparse graph. Different sense of the word sparse. It's just a cycle. I mean, there's not many edges. And the other side is still dense. Okay. All right. So, who would say this has high sparsity in the middle? None. Not a popular choice. How about medium? Okay, let me first ask low then. How about low? Okay, so n minus 1 chose medium. Okay. And it's always a different one. All right. Now, what about conductance? Sorry. Who thinks it has high conductance? None. Who feels like it has medium conductance? Uh, and okay. Well, we'll just double check. Who thinks it has low conductance? 1. Okay, so I got this wrong. Okay, n minus 1. All right. All right, last one is just a click now. Complete graph. Who votes for high sparsity? Here, it's like 2n over 3. Who votes for medium sparsity? And who votes for low sparsity? Okay, that's our most inconsistent one yet. All right, lastly, conductance. Who feels like it has relatively high conductance? And then medium and low. Okay. It's gonna be like an SAT problem, like given this info, what is n? Okay, all right. I don't know if it's consistent though. I don't know if there is an answer. Probably not. Okay, so let's go through these. So if I'm looking at this, sort of roughly a dumbbell graph, but 2 clicks, the first column attached by 2 edges. Most people thought it had low sparsity, but why? What would be like a very low sparsity cut? Yeah, remove those 2 edges, and then you have a lot of vertices on both sides. Okay, let's jump to this though. So people thought generally the feeling was that this had higher sparsity than here, right? Because we have more mediums than lows. Okay, so what would be like a minimum sparsity cut in this graph? The same cut. But with sparsity, you're just counting vertices on each side. So actually the sparsity will be the same for these 2 graphs. So whether you felt that was low or medium, it should have been the same. Okay? So that means that n minus 2 of you at least were wrong. But I think it actually was all n because I think it was different. It was a different one. Oh no, no, it's probably n minus 2 of you were wrong. Okay, fine. Now, contrast to the conductance. Okay, so conductance, most of you thought low, and I guess the same cut is a pretty low conductance cut. In fact, the conductance value will be less because you're counting edges instead of vertices, there's more edges. Okay, but most of you thought that there would be higher conductance here than here. Okay, why? Yeah, so the right part, although the same number of vertices, has much fewer edges. So the volume of the right-hand side is actually much smaller. That pushes the ratio up. Okay, so that's sort of 2 ways they differ. All right. So a click. Okay, so a click is basically going to have maximum sparsity. As most you can do it with an unweighted graph. Okay, so high is basically the right answer. And for conductance, okay, this is basically roughly as big as possible too. Okay, so that's fine. The real distinction is coming in the first 2 columns and seeing that this is actually not so much a high conductance or low conductance graph because you're actually worried about where are the edges. So conductance is about splitting up the graph so roughly you have the same number of edges on each side, whereas sparsity is trying to split up the vertices. Okay, so they have different applications algorithmically. One you're doing divide and conquer on the number of vertices, the other on the number of edges. So there's sometimes some are better than others. Okay, of course we're going to focus more not on these algorithmic applications, but on random walk stuff. Okay, so we're going to have to make some connections ultimately to some spectral properties. So let me just quickly remind us that for an undirected graph, we can model it as this matrix, okay, called the Laplacian. And one way to think of what the Laplacian does is it's taking some sort of vector of potentials on the vertices and evaluating the differences across each edge squared. Yeah. Okay. Yeah, so I should say that the sparsity of a graph is defined as the minimum sparsity over all cuts. And the conductance of a graph is defined as the minimum conductance over all the cuts. So, yeah, so it is true that if you just pick off the one on the side, yeah. And from a divide and conquer standpoint, you are going to look for like the best way to split it in half, right? So when we say that the middle graph has kind of moderate to high sparsity, we're saying, okay, it's actually tough to do divide and conquer on the vertices, and yeah, you pay a lot more in terms of the edges. But divide and conquer on vertices is just as easy for vertices, but not so much for edges. You're not splitting the edges up so much when you take away those two. Okay. Anyway, so we had this matrix. We studied it last time. XLX is the sum of squares. Another notation was that we let capital D be the diagonal matrix of degrees. Okay, that'll be used again and again. An alternative way to define, interesting, that looks like the same thing. Okay, all right, an alternative way to define the Laplacian is as the equation D minus A, where A is the adjacency matrix. Okay, and one way you can verify is just to look at one edge, E, right? So if E was the edge between U and V, okay, then remember LE was this, could be written as this outer product of like an indicator variable of U minus indicator variable of V. Okay, which looks like this matrix that basically has zeros everywhere except in the U and V column. Okay, you're going to have a 1 here, a -1 here, a -1 here, a 1 here, and 0 everywhere else. Okay, so the ones here give you sort of the diagonal 1 degree for just one edge, right? And the -1 is the adjacency of just that one edge. Okay, so that verifies L equals D minus A for one edge, and now in general L is a sum of edges, and you get sum of D's and sum of A's. Okay, that'll be convenient. All right, so how does this tie to conductance? Well, let's focus on a set S, which is the smaller side. So volume of S is smaller than the volume of the complement. Then, okay, so this is sort of a convenient identity. So if I look at this expression, right, we have this is equal to summing over all the edges E equals UV, the weight of E, and then you're going to be like a 1 if U is in S, minus a 1 if V is in S, so to speak. Otherwise, it's 0. Okay? So, squared. Right? So, if U is in S and V is in S, you just get 0. That term disappears, right? So you don't get any points for that edge. If U is in S and V is not in S, then you get 1 minus 0 squared. That gives you 1, and you get to sum up the weight of the edge. Okay? So, this expression 1L, 1L, applying L to kind of the indicator variable vector of S, will count the weight of the cut. Okay. Likewise, if you were in the denominator, this 1's S, you're just summing over the vertices in S, the degree. Okay, so the denominator, you just get the volume. That's more straightforward. Okay, fine. So whatever, there's some, at least you can take this conductance thing, which is a natural thing to study, and I guess write it in a slightly more fancy form. using some linear algebra. Nothing really has happened. Okay. Now, but that motivates the following definition. Okay. Let's define the normalized Laplacian, okay, as taking the Laplacian and sort of applying the square root of d, negative square root of d, or inverse of square root of d on both sides. Okay, it's sort of like dividing out the degrees in some linear algebraic sense. So one way to interpret this is, in general, if I'm looking at some expression like ymy over yy, which corresponds to things like eigenvectors of m, okay, that's equal to xlx x dx for y is equal to d to the 1/2 x. Okay, I mean, that's just a substitution, nothing too deep, but what's kind of already starting to take form is, in the top left, I'm sort of interested in the conductance, okay, and algebraically it sort of starts to take the form of, some kind of eigenvector computation relative to m. Okay, and sort of always what's kind of going on is eigenvalues are full of secret information. If we can make some connection, then maybe something magical will happen. Okay, so we're just trying to make some of these connections. Okay. All right. So towards further connections, this is a slide from last class. So just a reminder. So we're studying this randomized walk matrix, and we wanted to kind of pull out some information about its eigenvalues, but the problem was it's not symmetric, so we couldn't use our tools directly. But we did notice that if you, adjust r a little bit, like this d to the minus 1/2, r d to the 1/2, then you get this matrix Q that is symmetric. Okay, this matrix Q we call the normalized random walk matrix, and so it had this nice, decomposition into orthonormal eigenvectors, and we knew lots about it, right? That was sort of the first step towards unrolling everything and eventually pulling out that spectral, that convergence rate based on the eigenvalues. Okay, but now, so that's what we used it for. All right, so let's take these two things, right? Okay. So our normalized Laplacian was d to the minus 1/2, L d to the minus 1/2. Okay. And here we're going to use this identity I briefly mentioned. Okay. All right, so that looks like I minus d to the minus 1/2 a d to the minus 1/2. And what is that? Okay, I minus q. Okay, so, all right, there's this nice little connection that's come up. And we can even expand that further and write this as d to the minus 1/2 I minus r d to the 1/2. Okay. All right, so that's just kind of some plugging algebra. Again, it doesn't feel like we did much, but we're making connections. Okay, so, all right, so when I've rewritten a normalized Laplacian as d to the minus 1/2 I minus r d to the 1/2, what does that say about the relationship between m and I minus r? They're similar, and in particular that tells us they have the same eigenvalues. So there's something structurally very similar about these two objects then. Okay, some normalized version of the Laplacian and something that's basically the random walk matrix, right? Like doing I minus r, you can reverse engineer and figure out r, right? I is sort of a benign. Okay, so we've established that m has the same eigenvalues as I minus r. We also know a lot about eigenvalues of r and stuff like that, right? So if you have an eigenvalue lambda for m, it goes to what eigenvalue for r? So there should be some correspondence between right now we have a direct correspondence between eigenvalues of M and eigenvalues of I minus R, right? But the eigenvalues of I minus R are going to be closely tied to the eigenvalues of R because I is just the identity matrix. Okay. So in particular, if you have an eigenvalue for lambda for M, that tells you that R has some eigenvalue, which is a 1 minus lambda. Let's see if that's what I wrote. I wrote lambda minus 1. Oh, you think it's lambda minus 1? Okay. All right, so if mx is equal to lambda x, then rx is equal to I minus m x. Oh no, did I do it backwards? No, it's... Well, maybe you got it right then. Maybe this should be 1 minus lambda. A sign should flip anyway, right? Because you have m on one side and negative r on the other, so I think it's 1 minus lambda. Okay, all right, vice versa. If you have an eigenvalue lambda for r, what eigenvalue does that give you for m? It's also 1 minus lambda? It doesn't matter what I wrote. Okay, well, let's just hope everyone's right. Okay? All right, so, but here's maybe another question. If I know that the eigenvalues of m are equal to the eigenvalues of I minus r, what is the smallest eigenvalue of m? And why? Okay, negative 1 and why? No, wait, it's not a number. Okay, so we know that the maximum eigenvalue of r is 1. That corresponds to the stationary distribution. That'll give us our minimum eigenvalue of 0. That also means that the maximum eigenvalue of m is at most 2, because the minimum eigenvalue of r is at least negative 1. Okay, so we have this nice correspondence. Alright, here's this thing that we're really going to spend most of class focusing on. That's going to start tying some things together. Alright, so it's called Cheeger's inequality. We're going to let lambda 2 for the rest of the lecture be the second smallest eigenvalue of m. Okay, we can compute the second smallest eigenvalue of m. There's an eigenvector computation. Okay. The claim is that the conductance of G is sandwiched in between the second eigenvalue divided by 2 and, somewhat unusually, the square root of 2 times the second eigenvalue. Okay. The conductance of G is between, roughly, the second eigenvalue and the square root of the second eigenvalue. Okay. All right, so, this turns out to be very useful. It's also going to give us an algorithm to get a cut whose conductance is close to the second eigenvalue. We'll discuss that. But just taking a step back conceptually, it's sort of amazing because it's connecting a combinatorial property, something that sort of makes sense. I can draw a picture demonstrating conductance, right? With algebraic properties that are sort of magical and mysterious, right? Okay, so this is sort of amazing. Another important thing that I won't really discuss too much is that we're often interested in graphs where the second eigenvalue is pretty big. Okay, it's like a constant. It's still smaller than 1, but it's a constant. So if lambda 2 is a constant, okay, this actually gives us a constant factor approximation for the conductance, which is very useful. So this applies to a class of graph called expanders that'll come up in some future classes. Okay, it's actually the only way we know to certify a graph as an expander. Okay, because other algorithms, like things like sparsest cut, also can help you figure out if something is an expander. But we have a log-in approximation ratio for sparsest cut, so you can't really figure out if an expander because you kind of the log-in is too weak. But it turns out expanders are precisely the category where lambda 2 is big and roughly a constant. It's not too small. So if lambda 2 is really small, like 1 over square root n or something, then that square root really starts to hurt you. But if lambda 2 is a constant, just taking a square root is not a big deal. Okay, so that's another important thing, although we don't have quite the context to appreciate it. Okay, so before trying to prove this thing, which will be most of our effort, let me put some pieces together of what we've already discussed. All right, so here's the 3 pieces of the puzzle. From last class, the convergence rate has something to do with the spectral gap of the eigenvalues of the random walk matrix. Step 2, we have this mapping between the eigenvalues of M and the eigenvalues of I minus R, which has been corrected. Okay. And in step 3, we have Cheeger's inequality, which is relating the conductance of the graph to the eigenvalues of M. Okay. So you can already see, okay, at some level, okay, we can start from here. I start with conductance. I go to the second eigenvalue. Somehow from the second eigenvalue, I should get to some eigenvalue of R. And from some eigenvalue of R, I might be able to plug it in and say something about how fast things converge. Okay. So let's do that. Claim. So this is just a special case. We're going to have to figure out how to remove the condition afterwards. If the second eigenvalue is bigger than the absolute value of the smallest eigenvalue of the random walk matrix, which is, a negative number. That's why we take the absolute number. In the worst case. So then the convergence rate is something related to the conductance of the graph. Okay, so this one actually kind of makes sense. It's saying that a graph with very high conductance will converge to the stationary distribution very fast. What's a graph with high conductance? It's a graph where roughly you can't really split the graph. You can't split up the edge set into 2 parts without also deleting a lot of edges. Why does that also kind of make sense? Well, do you guys remember what the stationary distribution is for an undirected graph? No, not quite. Those are degrees. So if you're randomly walking on a graph and you've reached your stationary distribution, it's undirected, wherever you are is completely proportional to degrees, which is the number of edges you're incident to. So if you're kind of like, say, and so it kind of means that, what's the right way to? So something that something that has low conductance, right, will have like some set with very large volume, okay, and then a small cut, right? That would be a low conductance set, okay? But we can also interpret this large volume as large probability mass of the stationary distribution, okay? So at some level, if you want to converge to a stationary distribution, then you need to get into this bubble with large mass, right? But if you had a very small cut going into this large mass bubble, it would be very hard to get across potentially, right? So, but in a large conductance graph, that won't happen so much. And so sort of the places with lots of large probability mass also have lots of edges leaving it, and so things are going to kind of disperse and mix more quickly and stuff like that. Okay, so you probably had a sense that a high conductance graph is pretty well connected, right? Because you can't really divide the edge set in half. But here we also see why it's nice to have the volume in the denominator to some extent, because the stationary distribution is also proportional to volumes, to degrees. That's sort of some high-level connection. Okay, all right. That said, we are currently assuming this, and we're going to figure out how to address this and get rid of it in a moment. Okay. All right. So how do we prove this? I guess we can start with this thing is at most 1 minus gamma to the k times, the square root thing, right? Okay, so under our assumption, what is gamma? All right, 1 minus mu2 to the k, square root of some stuff. Oh, this should be a t, right? Okay. Okay, so right now we have some convergence rate relative to mu2. Okay. All right, so now I want to somehow connect mu2 to the conductance, right? So, I mean, just pattern matching, somehow that mu2 needs to become roughly conductance squared. Okay. So how might we go about that? Okay, but Cheeger's inequality uses lambda 2. Okay. Something like that. Okay. And then, yeah, so right now we have phi is less than or equal to square root 2 lambda 2. We can square both sides. Something like that. And then we get, whatever, negative. Okay. So this thing is at least something like that. Am I doing this correctly? Let's just be careful. Okay. Okay, yeah, okay, let's do it. Here's another way to roughly do the same thing. 1 minus, we'll see what I was doing wrong. 1 minus mu2 is equal to lambda 2. That's another way. Okay, and then this, okay. Oh, I'm sorry. Okay, I got it. Okay. All right, this was wrong. So this should have been 1 minus mu2 because of this silly definition of gamma. All right, so let's just do it more slowly. All right, so gamma is 1 minus, okay, there's two minuses in there. Is 1 minus mu2, which is lambda 2, which is at least this squared divided by 2, maybe? Okay, good. So now we have this is less than or equal to 1 minus square root of some stuff. And then here we get this e to the negative t phi squared over 2 squared of some stuff. Not sure why there's a factor of 4 there, but that's okay. This probably should have been a 2. Okay. All right. Fine. So, okay, all it's really saying is that we have this direct link between Cheeger's inequality and mu2. So if mu2 was defining the convergence rate because mu2 was bigger than the absolute value of mu n, then fine. We're done. So the only tough part then, of course, is what the hell we're going to do when mu2 is not determining the convergence rate. Okay. So in this case, we're actually not going to directly analyze R. So let me prompt this follow-up question. How can you change the random walk to force? Okay, so the issue is what happens when mu n is very close to -1, right? That's not good. Okay. So if mu n is very close to -1, then the absolute value of mu n is very close to 1, and you're going to have a bad convergence rate. Okay. So given a random walk, how might we force mu n to be sort of larger, farther away from -1. Not sure if this is guessable, but it does have a cute answer. Let me give you guys a chance. All right, so here's what we do. Instead of analyzing the random walk, we analyze a variant called a lazy random walk. It's like a random walk, except half the time you don't do anything. Okay. There's some joke to be said there, but I can't think of one. Okay, so each step I flip a coin. If it's heads, I stay. If it's tails, then I do a typical random walk where I choose some random neighbor or random edge and proportional to the edge weights. Okay, that's the lazy random walk. Why is that convenient? So in terms of kind of matrix notation, S is equal to 1/2 times the identity, right? Because half the time I stay there, plus 1/2 times R, because half the time I use R. Okay. All right, fine. It's going to have the same stationary distribution, of course. That won't change. Now, how does the lazy random walk help this question from before of trying to increase the minimum eigenvalue? Okay, so why? So if I look at, I'll say like mu n of S, I'll call that the minimum eigenvalue of S, right? It's going to be the minimum eigenvalue of I plus the minimum eigenvalue of R, or the average of them. So I won't change any of the eigenvectors and eigenvalues, right? Because it sort of any direction is fine for I. Okay. Now, we know that this thing is at least -1, and the issue is it might even be -1. But what's the minimum eigenvalue of I? 1. Okay. So that means this thing is at least 0, I guess. Okay. So the lazy random walk is going to have very nice eigenvalues, right? All right. So what about mu2? Okay. So if I looked at mu2 of these things, okay, what's the second eigenvalue, the second biggest eigenvalue of I? Okay, it's at most 1. Plus whatever was the second eigenvalue of R. So it's going to be over 2 kind of thing. Okay. So, all right, so now what we're going to do is we're going to prove I think this is actually where divided by 4 might come in. Okay. We're going to actually prove this. Now we don't have to have any qualification about the second eigenvalue, because at some level that's addressed by the stationary. So this capital S is by the lazy random walk, denoted by capital S. Okay. So, all right, so I think we proved this in roughly the same fashion as before. Okay. So we know that the second eigenvalue of S is definitely 1/2 plus the second eigenvalue of R. So if we had the gamma for our lazy random walk, I'll write it gamma S. Okay, this is 1 minus 1/2 plus mu2 over 2, where mu2 is referring to the second eigenvalue of R. Okay. Something like that. Okay. And then what did we show last time? I don't want to do it again. This is at least the conductance of the graph squared over 2. Okay, that's where we got our 4. Okay, and then we plug that in, and that's that. Okay, so the conductance is related actually not necessarily to the convergence of the random walk, but to the convergence rate of the lazy random walk, which is similar. Okay, all right. Okay, so fine. Okay, so that's really a big, important, high-level motivation of Cheeger's inequality. Is it's really the bridge that connects this combinatorial property of conductance to convergence rate of the lazy random walk. And so that kind of tells you something about how graph structure controls some probabilistic stuff about the graph, right? These are kind of hard connections to make. Okay. All right, so the rest of the class then is going to be focusing on the second inequality, which is the harder one to prove. The first one, I don't know if it's easy, but it's definitely easier. So I typically give it as a homework problem. That's probably has a whole Wikipedia article about it if you really wanted to, but I think if I give you some hints, you guys would be able to sort it out yourself. Okay. All right. So okay. All right. So we have 25 minutes left. All right. All right. So I want to show that the conductance is at most the square root of the second eigenvalue of the normalized matrix. Now, I know that the normalized Laplacian is again a symmetric matrix, so it breaks down into something like this. Okay. We also know the first eigenvalue is 0. Here the eigenvalues are listed in increasing order. The VI's are orthonormal. Okay. We also know that V1 corresponds to sort of that eigenvector for R. Okay, so if you just believe me, last time we showed that V1 must be square root D over 1's D. Okay, that's just plugging in some stuff we did last time. All right. And, okay, so that means that if I wanted to figure out what lambda 2 is, right? So lambda 2 is the second smallest eigenvalue. So I can try to minimize just this thing, YMY over YY, which is really minimizing YMY over unit length Y's. But if I don't have any constraints, then it's just going to pick V1, right? Because that will give me the 0 value. So it'll just pick square root D, okay? But if I force Y to be orthogonal to V1, then it has to basically pick only combinations of V2 through Vn. And in that case, it will pick V2. Okay. So if I look at this optimization problem, which is minimizing YMY over YY subject to Y square root D equals 0, we'll get lambda 2. And as noticed before, we can also write that as XLX, XDX subject to X dot product D equal to 0. Okay. What's important about this is that this is an eigenvector computation, and you can get X from Y, so you can get X. You can solve this problem. Okay. There's a MATLAB subroutine to do it for you. Okay. All right, so you get this vector X, right, which has some connection to lambda 2, right? We kind of know at a high level a couple things. Lambda 2 is one of our targets. We know that this expression reminds us of conductance from before. Okay. Okay, and that's fine. Now our goal is going to be to convert X into some subset with good conductance. Conductance square root of lambda 2 or so. Okay. But the question is how? And this is something you guys might try to guess. I have a vector X, and I want to turn it into sets of vertices. Vector X assigning values to the vertices. How might I try to extract a set?
Each coordinate of X should correspond to whether one vertex is in the set or not. Right?
Yeah. So all you have is kind of values for every x, for every vertex. X has a value for every vertex.
So it would be 1 if the vertex selected is 0.
Well, x is just a real valued vector. There may be negative values in there, positive values. It's an eigenvector of m. They're just trying to guess an algorithm because we've done something similar before. That's why I thought you guys might be able to guess it. Why it works is a different question. That would be harder.
My initial thought is we probabilistically set vertex I to be in the set with probability xi.
But it could be a negative number. So that wouldn't make sense.
So
It's negative, just not x. It's positive, then that's
Okay, so you can split between positive and negative coordinates. That's a reasonable idea. You can generalize that. Well, normalizing will still have the same positive and negative coordinates.
we square x and then we'll like square each coordinate and then multiply.
Yes, but in every and then randomly sample. So you're sampling in proportion to xi squared.
Yes.
Uh, sure. Um, so intuitively, x. Hmm? Okay. So another situation this arose was when we did some line embeddings with flow and cut problems, right? So we could interpret x as a line embedding, and that's what we're going to do. Okay. So we're going to treat x as a line embedding, sweep over it, and the claim is that you can find some cut relative to this ratio for x, which for our particular x will give you lambda 2. Okay, so that's the claim we're going to prove. If x is orthogonal to D, then we can find some cut with conductance related to what's called the Rayleigh ratio. Okay. For us, that's just lambda 2. I'll probably just assume x is that second eigenvector for the rest of the lecture. Okay, so we're going to try to prove this thing. I've broken it down to 4 lemmas, and I think this is the shortest proof of this thing out there. Worked hard to really trim it down today. Okay, but here's probably the most important claim. It'll make more sense why it's useful maybe later because it has some conditions that maybe seem out of the blue. So I'm going to let capital V denote the total volume of the graph, not to be confused with vertices, as usual, bad choice of variables, names by me. Okay, so let x be a non-negative random variable so that if I look at the support of x, which is the coordinates that have a non-zero value, it represents less than half of the total volume of the graph. Okay, so x is really positive for a small, less than half of the graph by volume. Okay, and the rest of all is 0. Okay, the claim is that xlx is at least the conductance squared over 2 times the volume. Okay, x dx is actually the volume of, it's the weighted volume of the coordinates in the support. Okay, forget the volume. X dx is something. It's some quantity. Okay, fine. But let's do this. Look, we only have 2 pages left. 1 page front and back. Okay, so, all right, let's, okay, we have some space. Okay, so this is probably the most interesting part of the proof, and then the rest is going to be, how do I get one of these vectors x? But this is the part where, as you can see, conductance will come into the picture. Okay, so, all right, off we go. So I'm going to write phi x dx. Okay, and if, here's what we're first going to do. I'm going to number the vertices V1 through Vk. So in particular, I'm only going to worry about the vertices with positive value. Okay. So support of x, again, if there's any confusion about the term, the support of x is the coordinates I where xi is greater than 0, or really non-zero. Okay, so this is only the subset of vertices with non-zero values. So I'm going to number in V1 through Vk decreasing in their value. Okay, so V1 should be the largest value, Vk should be the smallest non-zero value, and then the rest are all 0. Okay. All right, so if I look at this expression, the conductance times x dx, then this would be summing up over all of the non-zero coordinates, which is only those k. I guess this conductance will stay on the outside. Xi squared times the degree of Vi. Here, Xi is corresponding to Vi. I'm writing Xi instead of X of Vi. Okay? So we can write this as like a telescoping sort of thing. Xi squared times the volume of Si minus, I'm going to let Si equal to the first I vertices in this ordering. Okay. All right, volume of Si minus the volume of Si minus 1, because I'm only adding the ith vertex, which carries degree Vi. Right? Okay, so by telescoping stuff, this is equal to the sum of I equal to 1, k minus 1, volume Si, and this should be xi squared minus xi plus 1 squared. Okay. All right. Okay. Here now is your guys' chance to shine. I want to get rid of this conductance term. How can I get rid of the conductance term? It's going to be a less than equal to.
Can you just put in the conductor of each constant and then do that into this?
Okay. Well, sorry.
Conductor is the minimum, so you just expand it back to each of them.
Yeah, okay. So in particular, I want to take, so this times this is less than equal to, for each I, by definition of conductance. Okay. All right. Okay. So so if I sum over all the edges, E, say an edge between U and V, okay, I have the weight of E, okay. So if I have an edge between two vertices of my line embedding, right, it's appearing in the cut for like everything in between, okay. And so I get some like xi plus 1 squared minus xi plus the next one, where you get a plus and a minus, a plus and a minus, a plus and a minus. They telescope and you just get the outer endpoints subtracted. Okay, so you get Oh, so we have some confusing notation. Okay, that's okay. XU will be the youth coordinate, okay, minus XV squared. Okay, so this is coming from telescoping in each edge appearing in those terms. Okay. And then here comes the moment you've all been waiting for, which is where you get to use the Cauchy-Schwarz inequality. Okay, so if you guys don't know, UV is less than or equal to norm U, norm V. Okay, and okay, so each of these is like a WE XU minus XV, XU plus XV with some absolute values around it. And maybe I can write that as square root WE times square root WE kind of thing and kind of put one, okay. So you get this two square roots. One is summing over all the edges, E equals UV, the weight of E, XU minus XV squared, okay. And the other is summing over all the edges, WE, XU plus XV squared, okay. Now this term can be written more compactly as XLX, okay. And for this term, first of all, a plus b squared is less than or equal to 2a squared plus b squared. Okay, so I get some square roots summing over all the edges, we xu squared plus xv squared, okay, which Lx, this is actually x dx. Oh, there's a factor of 2 here. There's a factor of 2. Okay. All right, so what's maybe going on at a high level? Line embedding, telescoping. Interesting step maybe comes here where we get to use conductance, and that brings us to cuts. Okay. And the cuts get us into this form. Okay. And then, which is close but not the same as XLX. So this is sort of an important distinction, right? That part with the absolute value, it would be great if that was XLX, but it's not quite. We have to use Cauchy-Schwarz, and then we got kind of one part XLX and one part XDX times a factor of 2. Okay? And then, okay, if you divide back out, then you'll get the claim. You square both sides and you work it out. But what's I think really important is just to point out, this squared here, right? And that leads to the square root lambda 2 later on. It's quite unusual for us, right? I'm used to more like, I have a log in approximation. I have a factor 2 approximation, factor 3. The square root approximation sort of doesn't make a lot of natural sense, intuitive sense. But why does it arise? We pay for a square root when we take the Cauchy-Schwarz inequality, and that's killing us. It's just kind of important. It has it kind of has a lot of implications because this problem touches a lot of stuff in theory, and it all kind of comes down to this one moment where we had no choice but to use Cauchy-Schwarz. And that introduced this square, which tortures us for many other problems later. It would be great if we didn't have that square root lambda 2 in that bound. If I had just lambda 2 or something, that would solve all of life's problems. Okay. I have a limited set of problems in life that apparently could be solved by getting rid of Cauchy-Schwarz. Okay. All right. So now we just have to figure out how to get this this vector x. Okay. So we have 5 minutes. Okay. So this is actually not so hard to prove. So what I will do is I'm going to present the next piece of the puzzle, which actually these are relatively easy to prove. So maybe I'll leave it in the notes and just focus on the idea so we can finish in time and then put everything together for the fun part of the proof. So step 1. So if x d is equal to 0, x times d is equal to 0, then if I take x and shift it by the all ones vector, so x plus alpha ones for any alpha you want, positive, negative, it's only going to decrease this ratio. Okay, so I only point out the ideas. If you look at the numerator, adding the all ones vector, subtracting the all ones vector doesn't change anything because you're only looking at the difference of the endpoints squared. So if both of the endpoints go up, nothing changes. If both the endpoints go down, nothing changes. For y dy, because xd is equal to 0, sort of y dy is equal to x dx plus x d1s, two of them, plus alpha squared 1 d1s or something, right? But that middle term, d1s, is just lowercase d, and xd is equal to 0. So the cross term disappears, and you're just paying this penalty of alpha squared 1 d1 for any value of alpha. Okay, so that's all there is to that. Okay, here this one is not too crazy, but maybe it's better to leave it as a black box, but I can at least explain. Okay. All right, let's take any vector x and write it in terms of its positive and negative parts. Okay, so x plus keeps all of the positive coordinates and sets everything to 0, else to 0. X minus keeps all the negative coordinates and sets everything to 0. Okay, so and then flips it upside down or something, right? So I can write x plus minus x minus where right, they're both non-negative vectors. Then it's not too hard to work out some calculations and show that xlx is at least actually the sum taken apart, and x dx most the sum together. Okay, this would be just calculations, not too much going on there. I think it's more fun to see it come together. If we have time, we can come back to this. Okay, I left some space for proofs, but okay. All right, so this is maybe where it's more fun. All right, so this is really the only three pieces of the puzzle you need. The key thing, if I can get some non-negative vector where the support represents less than half the volume, then I'm going to find that cut I need. Or I'm going to get the, okay? And then to try to get this vector, so I want a vector x where the positive coordinates represent less than half the volume. Okay, I have two tricks at my disposal. One, I can sort of split x into two non-negative vectors. Okay, and also I can shift things. Okay, all right. So right. Okay, so I'll get you guys. Well, okay, so here's maybe a natural way to start. I can write okay. I can start with xlx, and I can always break it into the positive and negative parts. Okay. Okay. And it would be great if I could apply the lemma. Let's see what would happen if I do. The reason I can't apply the lemma is because I don't necessarily meet the conditions. Okay. But if I did apply the interesting lemma, if we just pretended that the supports of each of those vectors were nice, okay, then we would get, this is at least the conductance squared x dx, x plus y plus x plus dx plus. No, okay, these pluses should be minuses, shouldn't they? I'm just like writing the same thing over and over again. Something like that. That would come from the interesting lemma. And this is at least phi squared over 2 x dx. Okay. And where would I go from here? If I wanted to relate lambda 2 to the conductance. And that's what we'll get what we want. I mean, you take the square root is how I presented it earlier. Okay, so that would be great if I was allowed to do this step. Otherwise, it's kind of straightforward. Granted, we skipped some calculations, but again, those calculations we skipped weren't the hard part. This is maybe the harder part. So, okay, so I can't necessarily apply it to x. So what can I do about it? Okay, so the issue, right, is that I split it up into positive and negative coordinates, but it's possible that maybe there's too much volume on the positive side or there's too much volume on the negative side. Actually, one side will be good because they can't both have more than half the volume, but the problem is that one side might have more volume than the other. I need to get to a state where roughly both sides have half the volume. So let's say I have too many positive coordinates. I have a lot of positive coordinates, only a few negative coordinates. We can shift. Okay, so, we're going to let y equal to x plus alpha 1s, such that, the volumes are good. Okay, now you apply y to all of that, and you'll end up with yly over y dy is at least conductance, and we know that shifting is only going to decrease the ratio. Okay. All right, so that's roughly the proof of the Cheeger's inequality. I'm going to give you guys one more question. I didn't actually show that the algorithm works. So we proved Cheeger's inequality, okay? But I didn't actually show that the algorithm works. Any guesses as to how to adjust the proof to show the algorithm works? Okay, let's see if this is set up. Okay, so the idea is as follows. So if I just wanted to adjust the proof slightly, okay? So in this lemma, I assume that all of the sweep cuts, we just said, all cuts have conductance at least this thing, phi, so then we get this phi squared. But if I said, okay, suppose all of those sets, all of the, I guess I'll call it line cuts, have conductance, at least some alpha, some parameter alpha, then this would have become an alpha squared, right? It would just get plugged into here, and just phi's become alpha. Phi was an obvious lower bound because that's the conductance of the whole graph, but maybe it's something bigger like alpha, right? So that's the best conductance you get from any of your line cuts. You go all the way back into our proof down below, and again, these psi's become alpha, and then so instead you'll get alpha squared over 2, where alpha is the best conductance of all of your line cuts, right? Which means that your best conductance is at most square root of 2 lambda 2. Okay, so if I just plug in, out of all the line cuts, what's the best conductance I get? Call that alpha. Then you'd say, okay, now the best conductance I get is at most square root 2 lambda 2. So it's really the same thing as we just proved. Okay, all right, so that's it. That ties conductance to rates, and I'm late.